Hi everyone. For today's class, we'll talk about interesting topic na. This time very different from the other lessons no that we discussed, because this time we'll talk about not the lives of other people, okay, not their lives, okay, but we'll talk about real people related to this topic, okay, at the last part no of this presentation, no? Fundamentals of data science, no? So this, I think, the fifth, yeah, the fifth lesson for this term, because last time we talked about algorithm analysis, no? And then before that we talked about mathematical preliminaries, and then before that data science, no? Again, we're here. We're talking about data science again, fundamentals of data science. And then before that we talk about data analysis. This is the first, no? So this is the fifth, no? So in the second lesson, we don't, yeah, we defined it, but I think we just gave a single definition of data science. Here we'll have a lot of definition of data science, and we'll understand it better this time, because last time we only talk of like data science is not like it's not a computer, no, it's not computer science, it's not statistics, no, and not even natural science, no, but we can use the tools, no, we can use the tools from computer science or from mathematics or from statistics, no, in data science, no, in analyzing our data, no. But of course data science is not about analyzing data only, right? Since, as we mentioned during the first two lessons, that data science is broader than data analysis, right? So it's just one aspect. So here we'll learn more about, again, data science. And the last part, those people who deal with data science, no? Which we call data scientists, no? So we will know more about the anatomy of data scientists, the last part of this lesson. Okay, so let's dive into the major topics. Now to the next slide, telling us the major topics that we will be discussing for today. So again, data science, then big data applications, and data scientists, as I mentioned, no? So let's dive into the first part, data science. So what is data science again? Okay, the term data science has been traced back to 1974, when Peter Naur proposed it as an alternative name for computer science. Okay, the definition of data science can be seen as the extraction and transformation of raw and unorganized data into information processed and usable by companies. By this time, you should have realized this, right? You should have realized, no, that this definition of data science, no? Now, data science is a scientific discipline aimed at establishing statistical and mathematical models in order to analyze and extract large volumes of data for their use, no? So that it will be useful, we need this, no? We need to establish these models, no? I believe by this time you know that already, but not yet concrete, no? We will concretize this in the following lessons, no? Actually, in the next 5 weeks class, we'll focus on statistics, no? So there we'll see an example of this mathematical model in the next 5 weeks, starting next week, no? Our focus now is statistics until the 12th week, no? On the 13th week, yeah, it's not anymore related to statistics, but again, also interesting topic, which is knowledge representation, no? Knowledge theory. And that's the last lesson, no? And you'll have your final exam. Okay, class? But of course, you should have your midterm exam first, no, before your final exam. And I suppose you just finished your prelim exam, right? Okay, anyway. Now, so data science, we know already it's multidisciplinary, right? Because of those two lessons, no? Or those 4 lessons, no, that data science, no, multidisciplinary, meaning it makes use of mathematics, right? Remember that lesson on mathematical preliminaries, no? Statistics, as I mentioned, in the following weeks, yes, we will focus on that, statistics. Data analysis, which is the name of this this course. Then computer programming, which is I think your course is related to this, computer related course. Information theory, and so on. Okay, some of you, I think, information technology, right? Course. Okay, class, so it's a multidisciplinary, no? But later on, we'll realize not only this, no? That's why it's etc., no? Not only this. Okay, so what else can we talk about data science? Yeah, we already know, right? The data science deals with theories, models, algorithms. In fact, last lesson about algorithm analysis. No, the theories, yeah, self-explanatory, right? The models, you have an idea, of course. However, we'll concretize this in the following weeks now when we focus on statistics, no, and analytics, big or small. Later, we'll discuss more about this analytics, no. So it's about analytics and applications and a scientific approach to using data based on well-founded theory and sound business judgment, because it has use in business, no. And you learn more about this on the third part when we talk about big data applications, no? Big data applications. Data science is more than the mere analysis of large data sets. As I mentioned, it's not just data analysis, right? Data science, no? Now, it's mentioned here large data, no? Large data. But usually we use big data, no? In our context, we use big data, but I mentioned to you large data also, right? So in our context, we can use big data. So it's not just analysis of large data sets, it's also about the creation of data. So the field of text mining expands available data enormously, since there's so much more text being generated than numbers. The creation of data from varied sources and its quantification into information is known as datafication. I'd like to talk more about this text mining. Remember the data analysis methods that we talked about? I think in the first lesson, right? Data analysis methods. We talk about the text analytics, right? And also data mining. There are 4 of them. No? So this is like a mix of the two. You mix the two, you combine the two. Text analytics and data mining. This text mining. But the focus is more on the text, no? On the text. Remember, when we talk about text analytics, our data there coming from the text messages or messages from the Viber or from the FB Messenger, no? So not numbers, but text, no? That's why we have this field, because there's so much more text being generated, no, than numbers. As I mentioned, this text may come from what? From the FB Messenger, as I mentioned, no? Or from Viber, or from your device, no? So there's this field called text mining. In fact, because of this, there's a need to introduce this term, no, datafication, quantification of data, no, wherein this data coming from varied sources. But of course, they can be numbers also. They can be numbers, but varied sources meaning not only numbers but also text, no. Okay, so we also know this already, that data science is also more than machine learning. In fact, it's more than AI also, no? Artificial intelligence. So that's the first part of this lesson. Okay, let's go to the next part of this lesson, which is about big data. Okay, class, so let's talk more about this big data. Actually, it's the same thing as large data, no? It's the same thing as large data. But this is more commonly used, no, in this field, no, of data science, big data instead of large data. Okay, among all the new buzzwords in business, and there are many, big data is one of the most often heard. The burgeoning social web and the growing role of the internet as the primary information channel of business has generated more data than we might imagine. Okay, that's very self-explanatory. 87% of the US users upload an hour of video data to YouTube every second. 49% of population has heard of Twitter and 7% use it. Half of Twitter users are white, and of the remaining half are black. Twitter's users follow some brand or the other, hence the reach is enormous, no? And as of 2014, there are more than 500 million tweets a day. In contrast, 88% of the population has heard of Facebook, and 41% use it. Okay. Now, USC's Martin Hilbert calculated that more than 300 exabytes of data storage was being used in 2007. An exabyte being 1 billion gigabytes. Now, we're not so familiar with this, the exabyte. We're more familiar with gigabytes because GB, right? When we load our data, usually that's what is reflected on our phone, no? How many gigabytes, how many megabytes, MB. But exabyte, I think it's new to you, no? If not all, to most of you. So this is the volume aspect. Now we're talking of the volume aspect of the big data. There are other aspects of data. In fact, there are other V's of big data. We will talk about that later. No? For now, we have already talked about the volume aspect of the big data. No? So let's talk more about it. The scale of data generation is mind-boggling. Google's Eric Smith pointed out that until 2003, all of humankind had generated just 5 exabytes of data. An exabyte is 10,006 bytes, or a billion bytes. Today, we generate 5 exabytes of data every 2 days. So what's the cost? What's the reason for this? Okay, about this big volume of data, or this volume of big data. Okay, the main reason for this is the explosion of interaction data, a new phenomenon in contrast to mere transaction data. This interaction data may come from the one I mentioned already, from your text messages, or your messages from the Viber messages, or FB messages, social media messages, this interaction data phenomenon. So this to contribute to the volume of the big data, these two, interaction data and transaction data. Now, interaction data comes from recording activities in our day-to-day, ever more digitalized, such as browser activity, geolocation data, RFID data, sensors, personal digital recorders, such as the Fitbit and phones, satellites, etc. Yes, we now live in the Internet of Things, IoT, probably you heard about this, this IoT, Internet of Things, meaning our devices already connected, like a load of information. Your cell phone has a load of information, connected. We connect the devices to internet. That's the Internet of Things phenomenon, and it's producing a wild quantity of data, all of which we seem to have an endless need to analyze. So again, as I mentioned, there are other V's of big data. The other two are velocity and variety. So big data exceeds the storage capacity of conventional databases. That's why it's big data. If it exceeds the storage capacity of conventional databases, then we have that term big data. So this nomenclature was originated by the Gartner Group in 2001 and has been in place more than a decade. Okay, so so there, the three V's, Okay, so these are the 3 V's. Now let's discuss each of this. Now volume, yeah, we discussed that already in the previous slides. So it's the amount of data generated online and offline transactions in kilobytes or terabytes, save in records, tables, files. Now, variety, structured and unstructured. I think we talk about structured data, data structures in the first 2 lessons. Online images and videos, that can be data, a kind of data. Also, human-generated text. Remember the text mining, the text mining that we talk about, or the text coming from your device, or from Viber and so on, from social media. Machine-generated readings. This one from other machines, coming from other machines. So now, velocity, speed, of course, as the term implies, speed, speed of generating data. So this is connected to the internet, the internet provider, your internet provider, the signal, the connection. Okay, generated in real time, online and offline, in streams, batch, or bits. So now let's talk about these two. We talk a lot about volume. Now let's talk about these two. Okay, so first, the velocity. Data velocity is accelerating. Streams of tweets, Facebook entries, financial information, etc., are being generated by more users at an ever-increasing pace, to the point that we get overwhelmed with information. The information. Once we go to the we get overwhelmed, because we get curious, so we explore a lot, to the point that we get overwhelmed with the so many, especially if the speed of your internet is fast, is fast. So it is connected to data velocity. So whereas velocity increases data volume, often exponentially, it might shorten the window of data retention or application. For example, a high-frequency trading relies on microsecond information and streams of data, but the relevance of the data rapidly decays. Okay, so possible also that your internet is not fast, it's slow. Now, when it comes to trading, important that you receive information very fast, meaning microsecond. when you say trading class, it may be related to the like stock trading, you know, that the cryptocurrency trading, okay, the options trading, which involve which involve money, no? Involve money because it has to do with buy and sell, no? Buy and sell stocks, something like that. So sometimes you have to buy immediately, no? Otherwise, there will be a change of price. The volatility of prices, no? Very important to consider when you buy and sell. What if your internet is slow? Okay, so what will happen? The relevance of the data rapidly decays. No use. In fact, not only no use, but you also lose money. Okay, so there. So very important, the data velocity, no? So anyway, but it contributes to the big data, no? So next is the data variety. Finally, data variety is much greater than ever before. Models that rely on just a handful of variables can now avail of hundreds of variables as computing power has increased. Okay. Now, the scale of change in volume, velocity, and variety of the data that is now available calls for new econometrics, no? And a range of tools for even single questions. Okay. So now, so we don't just talk of 3 V's. Now we can also talk of 4 V's of big data. So what's the added V? Okay, let's find out in the next slide. So what's added? Veracity, no? So volume, yes, terabytes, records, transactions, table, files. These are the like the keywords, no? Keywords, key phrases are related when we talk about volume of big data. Variety of big data, though we discussed this already, just to reiterate it. Structured, semi-structured, unstructured, all of the above. This one is not mentioned, the semi-structured. Okay, how about the velocity, batch, near real-time streams, no? Okay, now the new one, the new V is the veracity, no? The authenticity, no? The truthfulness of your data, the trustworthiness, the origin, the availability, the accountability of data. Okay, important also, right? That's why here you can relate, you can connect here the fake news, right? Fake news is also data, but it's just fake, no? So that talks about veracity of big data, no? How truthful the big data, no? The data are. Okay, so not just volume, not just variety or velocity that we can talk about when we about big data. Question: are these the only V's that we can talk about? Okay, let's find out. Actually, no, right? We even have 6 V's of big data. Now, so what are the added 2 V's? So we have value and variability. No? Okay, so yeah, we discussed this already. This 4, no? This 4. So what's the value? It makes sense, right? This 2. The business value of the data collected. Because one reason is to use it in business, no? One reason for the big data, and we'll find that out later, no? When we talk about applications. So right now we're talking of big data. Now later, the third part of this lesson, we'll talk about the big data applications or the data science applications, no? But of course, not only in business, and we'll find out also that we use big data not only in business, no? Okay, so this is an important V, no? Important V. Business value of data collected. Variability looks the same as variety, no? Variability, but they're different, no? Because the variety, the types of data, whereas the variability, the ways in which the big data can be used and formatted, the ways, no? So it's different from types of data. Okay, so far these are the 6 V's, no? If you want to explore more on this, probably there are more V's, no? But for now, here we have until 6 V's. But the main class is this one, the 3 V's, no? Volume, variety, and velocity. Okay? But here, class, we're just talking of data. But data, as mentioned here, data is not information until we add analytics. Meaning, if we don't add analytics, it's just noise. So no use, no? No use for this. Now, even if we're talking about this, right? Volume, variety, velocity, no? Or even the veracity, no? Or the value or variability of data. If we don't add analytics, it's just noise. We'll talk more about analytics later, no? And even concretize this, no? In the following lessons when we talk about statistics, no? And more bigger data may mean more noise and does not mean better data, no? That's why you, right? Sometimes you have that feeling, no? When you go in the internet, no? And then you're searching about something. Yeah, it adds knowledge, no? It adds knowledge and the curiosity, no? It arouses curiosity. However, you get overwhelmed, no? With too much data. So somehow it's kind of noise, right? It's kind of noise to you, no? To the point that you just want to close your laptop, okay? You want to close your laptop because it also creates headache, no? So it also creates headache. So anyway, so data may mean more noise and does not mean better data. Okay? Does not mean better data. That's why when you do research, no, you really have to do that. No, you have to search, no, and even to the point you get overwhelmed. That's why you have to you have to be clear with your problem statement, no, so that you will only choose the data related, no, to your problem statement or to your study. Okay, so the others will be noise only, no. So you have to remove them, no, and then that's part of analytics, no? That is part of analytics class. So that the data will be useful, no? You have a better data and a useful data. How? So that you can create model. Okay, models. Okay, in many cases, less is more and we need models as well. Okay, I will be able to concretize model again in the following weeks, in the next 5 weeks, no? When we discuss statistics, no? Topics in statistics, especially that lesson in linear regression and correlation, no? Okay, so in a seminal paper, Halevi, Norvig, and Ferreira, 2009, argued that even simple theories and models with big data have the potential to do better than complex models with less data. So you notice the focus on data because this is data science. This is data analysis, no? Though we know data science is no broader than data analysis. But again, you do data analysis, no, in data science, no? So the focus is data. Otherwise, if the focus is on the theories models, as mentioned in the, where is that? In the first two lessons, it's not anymore data analysis or data science, right? It's something else. Okay, probably it's more of algorithm analysis, no? Though algorithm analysis is part, no, of data science or data analysis, no? So again, even if the theory or model is simple, as long as you base it on big data, may have the potential to be more useful than complex models, but based on less data. Okay? You'll find out later, no? Later, when we go to the following slides. And also in the following weeks. Na? Okay, Mankinsey argues that a successful data analytics plan contains 3 elements, no? Interlinked data inputs, analytics models, and decision support tools, no? Mentioned in this article, no? In March 2013. No? I'll show you a table on this 3. So these 3 elements, no? And once you have these 3 elements, what will be the result? Okay, so let's dive into the table. So this table class. So interlinked data inputs plus analytic models plus decision support tools equals business value. That's why that fourth V, no? That fourth V that we talk about in the 6 V's, no? Important, no? The value of the data. Okay, to the business, no? So so these are like your data class, big data. Okay, this is your big data, but more specific, no? Because you're talking of an industry, healthcare industry, no? But of course, you don't only apply this in a healthcare industry, in other industries as well, no? As we mentioned, there are a lot, no? Applications of this, big data. Later, you'll know more about that. Okay, anyway, so just to show you this, these 3 elements, no? These 3. So for the interlinked data inputs, coming from universal IDs, no, treatment data, cost data. And then based on this data, you can come up with a model, no? Analytic model, no? Like for example, this one, no? Disease management. So you can come up with an analytic model to predict. So that's the one reason, one purpose of the model, no? In fact, when we talk about linear regression and correlation, we'll talk about prediction also, no? Prediction. And in the following slides also later, we'll talk about prediction. Okay, predict hospitalization risk for individual patients. Okay, and then not only these two, no? You need tool so that combining these three come up with a business value, which is reduce spending on patients with chronic diseases. I want to read this class, no? This business value, no? If you do this three, and these are like, I'll leave this part to you, no? Leave this part to you. So more efficient, more cost-efficient care, right? That has a business value because in a business, of course, not only profit, no, but we want to lessen the costs, no? And also not only those two, but for human care, meaning for foundation, probably to help the society. So not all about profit, no? When there's a business, not all about profit also. Okay, these are like examples, no, regarding those three, no, that I mentioned, no? Regarding the focus of the business, and not only profit, not only the cost, but also human care. Okay, so next is reduce spending, na? For example, on unnecessary hospital stays, na? Reduce hospital budgets, increase share of successfully rejected claims, negotiated discounts or rejected reimbursement for selected drugs. So these are just examples, na? When we talk of business value coming from these three elements, na? And these are like the specifics. Okay, so I discussed the first one, so I leave the other part to you. Okay, class. So next is, yes, this one. This is a famous quote coming from a British statistician, George E.P. Box, one of the authors of this book, Empirical Model Building and Response Surfaces. No, we'll not discuss the details of this. No? Instead, we'll talk about the quote that that he cited. No, all models are wrong, but some are useful. But as I mentioned, we need models, right? So that our data will become useful, right? Remember the models that we mentioned. So that it will not just be noise, we add analytics, and in adding analytics, we want to create a model, no? A model, and we can concretize this in the following weeks, no? Particularly when we talk about linear regression and correlation. Model in the form of equation. And that equation talks about prediction. Prediction. Okay, but it mentioned here, all models are wrong. So what's the use? But some are useful. Okay, what's the meaning? Many people in the field of statistics try to develop theoretical models aiming to predict the behavior of a certain process. For instance, the selling trend of a product or the number of tourists in a city. Because purpose, profit. One purpose, only profit. But again, as I mentioned, don't get me wrong, not only profit, of course. If there's a business, not only profit, but also to lessen the cost and also for human care, no? Foundation to help the society, okay? But how can you help the society if there's no profit, right? Okay, so and how can you have a profit if you have more costs, large expenses, right? That's why you have to consider this three, na, in a business. For a business to have a value, as we talked about a while ago, na, thus the idea of this quote is that every single model will be wrong, meaning it will never represent the exact real behavior, but it's not really totally wrong, no? That's why it's mentioned here. Some are useful, no? Having said that, even if a model cannot describe exactly the reality, it could be very helpful if it's close enough. Otherwise, class, it's prediction. So obviously, since it's prediction, it's not 100% correct. That's why when we talk about this topic on linear regression and correlation, we'll talk about percent of accuracy. But we'll never talk about 100% of accuracy. But we will only talk about like less than, of course, no? And we'll talk about like some industries, it's okay to have at least 50% of accuracy of that model of prediction you use for prediction. It's fine to some industries. There's some industries cannot be. It has to be at least 90% accuracy. Not 100, at least 90. Because it involves human lives. Like you have to intake a drug, no? Something like that, human lives, about health of the people, no? That's why it has to be like at least 90. But if it's like to some like psychology or education models, sometimes 70% is fine, at least 70%, no? Okay, because if you execute that model or algorithm, it may not the life of a person will not be at risk, no? Will not be unlike when you're talking of like healthcare, probably, or in the medicine field, yeah, important that the model is at least 90%, especially if that model has to do with intake of the drug. Okay, so important. No, it really depends, but definitely it's not 100%. But still, even if it's not 100%, as mentioned here, it's still useful and helpful as long it's close enough. Okay. Otherwise, class, there's no need to talk about big data applications, no? If all models are wrong and nothing and all are not useful, no? It's good that we have this, no? It means that yes, all models are wrong, but not totally wrong. Okay, because it's mentioned some are useful. So that's why we can talk of big data applications, no? That's why that's our next part, no, that we will talk about big data applications. Otherwise, no need to talk about that if it's mentioned the models are not not useful, no. So again, having said that, even if a model cannot describe exactly the reality, it will be very helpful if it's close enough. So that this brings us to the next part of our lesson, which is the big data applications. So they have used, no? These models have uses, especially if we base the models on a big data, not small data, but big data. Okay, remember what's mentioned a while ago? Even if it's just a simple model, as long as it's based on big data, it's more useful than the complex model based on less data. Okay, so the focus is on big data, not small data. Okay, class, so let's talk about some applications. Some here are general, the others are specific, no? Applications. So let's dive in. So data science aims to extract actionable data from a large volume of raw data. By this time, it's clear to you already, right? Actionable data, meaning this actionable data can be in the form of a model, an algorithm, no, to help you predict or decide, make a decision like that, no, regarding the business, no, to have a profit, to have less cost, or for human care, no. But you base it from a big data, this large volume of raw data, no. Even if that model is is, as I have been repeating, simple, okay, as long based on big data. So the main objective is to identify trends and predictions from this data. With the rise of the big data, data science is developing more and more in all sectors of activity. Okay, and just to by this time you should have realized that, but just to emphasize that point, that in all you can use that in all sectors of activity. Let's have more examples, no? Generally and specifically. So in sales, data science will be used as a decision-making tool in order to identify the future expectations of consumers. For example, no, its purpose will be essentially marketing. Okay, marketing. Okay, so here you can see the tree, no? The tree, the profit, no, less cost, human care. Right? Okay. In the environment, data science will make it possible to model climatic phenomena to establish impact projections related to this phenomena. Okay. In transport, data science will be used to adapt the frequency of transport to the flow of travelers at certain times to avoid traffic. No? In health, data science will be used in toxicology, the study of toxins, body toxins, no? Bad to your health. Those are bad to your health. It's also currently used to fight against epidemic of COVID-19. So very current. Okay, in banking and insurance, data science will be used to analyze customer loss. For example, or to offer products based on customer needs. Okay, so this is a kind of general, no? General. Okay, let's discuss some specific examples. Okay, but before that, data science is transforming business, right? Companies are using medical data and claims data to offer incentivized health programs to employees. So these are like specific because of the numbers, no? Caesars Entertainment Corporation analyzed data for 65,000 employees and found substantial cost savings. Okay, Zynga Incorporated, famous for its game farm, you're familiar with this, Farmville, accumulates 25 terabytes of data every day and analyzes it to make choices about the new game features. So reason can be for, yeah, profit, definitely, right? But of course, it's still human care, no? Because this one, yeah, entertainment, no? Because people do not need also entertainment, right? So you talk about holistic, no, holistic, not only about work but also for entertainment, no? So this company contributes to that aspect, no? So it's not about profit only. That's why they want to change the features of the game, no? Or they want to have new game features, not only for profit but also for human care, no? Okay, UPS installed sensors to collect data on speed and location of its vans, which combined with GPS information, reduced fuel usage in 2011 by 8.4 million gallons and shaved 85 million miles off its route. So very self-explanatory, you know, this part. So now, things change when you have gargantuan data, so meaning big data, because almost all correlations become significant. So that's one reason also, class, why we want to base it on big data, because of correlation. No? We can get significant correlations. Now, what is this correlation? Actually, we'll talk more about this in the in statistics part, no, of this lesson of the of this course. That lesson about, I've been telling you this already, no, linear regression and correlation. No? But just to give you an idea, correlation is like think of a line, no, a line from left to right rises, no, a line rising from left to right, and then another line falling from left to right. No, the former has positive slope, the latter has negative slope. Okay, so if you have that line rising from left to right, which has a positive slope, it means that, for example, two variables, no, as the values of one variable, or let's say x and y, let's talk about x and y, as the values of x, no, increase, the values of y also increase. That's the that's the one with the positive slope. That's the line with, as you go from left to right, it rises, and that is called the positive correlation. Positive correlation. No? So the other line is the negative correlation, meaning if it has a negative slope, and then as you go from left to right, the line falls. No, it falls diagonally. It falls diagonally. So if you look at the values, no, as the values of x increase, the values of y decrease. So opposite, no. So that's a negative correlation. We can even talk of high positive correlation, moderate positive correlation, or even low positive. Similarly for the negative correlation, no? High, moderate, and also low. Okay. In class correlation, we talk of relatedness, no? That kind of relatedness, no? That I explained regarding the positive and negative correlation, but not causality, no? As mentioned here, no? And one might be tempted to draw spurious conclusions about causality, no? So correlation is not causality, no? It's more of relatedness. It's more of talking about high and positive correlation, no? I'm sorry, talking about positive and negative correlation, no? Based on big data, not based on small data. Gargantuan data is big data. Okay? For many modern business applications today, extraction of correlation is sufficient, but good data science involves techniques that extract causality from these correlations as well. So meaning, yes, you can extract causality from these correlations using techniques, but correlations themselves are not about causality. It's about relatedness, or your association between the two variables, but not cause and effect. When you say causality, it's not cause and effect. It doesn't mean the cause of x is y, or the effect of x. No, it's not like that. No. In many cases, detecting correlations is useful as is. So useful already in many cases. But in data science, when you say good data science, you can arrive at techniques to extract causality, no, from these correlations. That's also possible using other techniques, no? But when we talk of correlations, we don't talk of causality. That's something important to you to remember. In fact, you'll understand that better here. This is example of Google Flu trends regarding this correlation that we're talking about, that it's not causality. Okay, let's talk about this specific example. So for example, consider the classic case of Google flu trends. We'll see, I'll show you the next slide. Now the graph. The orange line, actually it's not orange line, it's more of a red line to me. It's actually US flu activity. And the blue line is the Google flu trends estimate. Okay, the figure shows the high correlation. Now, I mentioned to you about high. It's just that I mentioned about high positive, high negative. No, so when you say high correlation, can be high positive, high negative between flu incidents and searches about flu on Google. Okay, that's according to this, I don't know, to this author or these authors, no, in 2009. Okay, class, it's like this. So this one makes sense, no. For example, you have a flu. It's possible you want to know more about it, no, or not only you. For example, your friend or your relative, no, or your father or mother, no, or someone, no, related to you has a flu. Okay, there's a tendency for you to search it, no, on Google, how to treat the flu and so on and so forth, right? So in a way, it's kind of related to the flu incidents because you have flu. When you say flu incidents, those people who have flu, and you're one of them, for example, and you search about it. So somehow there's a connection, or you can associate the two. One variable is the flu incidence. The other variable is those people who search about flu. Flu incidence is the number of people who have flu. Searches about flu is the number of people who search about flu on Google. They have like a high correlation. And we can see the high correlation here in the next slide. So you notice all they're kind of overlapping, no, but they're not really overlapping. Kind of overlapping, no. Okay. Never mind the class, the sky blue. Just the blue and this red or orange, no. You notice the blue and the red or the orange, no. Like the same trend. Okay, yeah, we can talk of trend. It's like the same trend or the same pattern, no. But not cause and effect, no. We cannot see the cause and effect here. And really, this is like from big data, no? Actual big data in 2011, 2012, 2013. That these two variables have high correlation. You notice high because not mentioned about positive, negative. Remember, there's like a line here. If you draw a line here, it's positive slope, right? But if you go here, it's negative slope. That's why they did not talk about high positive, high negative. They just talk about high correlation, meaning if it's positive, high positive, still high, right? If it's negative, still high. Positive, negative, positive, negative. If you think of a line, no? A line. Actually, you'll understand what I'm talking about in the following weeks now when we talk about the linear regression. That's why there's a word linear regression. We use a line there, no? You use a line to approximate this graph. Okay, we like to find that line. Approximating, no? So anyway, so let's discuss more about this in the following slides, no? Obviously, searches on the keyword flu do not result in the flu itself. Of course, the incidence of searches on this keyword is influenced by flu outbreaks, as I mentioned, right? The interesting point here is that even though searches about flu do not cause flu, we all know that, of course, they correlate. Not the cause, but they correlate with it. You can associate the two variables. That's what we mean. We can relate the two, but not in a way that cause and effect. And common sense will tell you it's not the cause, right? Searching the word flu on the internet is not the cause of the flu, right? Common sense will tell you that. And many times even be predictive of it, but we can use it, that correlation, for prediction. Okay, we can use the correlation between the two for prediction. Be predictive of it simply because searches lead the actual reported levels of flu, as those may occur concurrently but take time to be reported. Okay, and how do we do that? That prediction model. We need a model. To be more concrete, we're talking of in the form of equation, which we will talk about in the following weeks. Now, in one of the following weeks, when we discuss about linear regression and correlation. In fact, what the equation that we're talking about is linear equation. Okay, very simple, right? Linear equation. Linear equation that you learned in high school. Okay, that we can use for prediction. simple model, right? Linear equation is simple model, but it will be very useful if based on big data. Okay, but in our lesson class in the following weeks, just to illustrate it, probably we'll not use big data, no, for the purpose of discussion, no. Anyway, I'll emphasize that. I will discuss more about that when we come to that lesson, no, when we're talking about that lesson already. Okay, and whereas searches may be predictive, the cost of searches is the flu itself, no. One variable feeding on the other in a repeat cycle. The cost of searches, no? But the cost of flu, it's not the search, no? Probably the cost of searches, no? But not the flu. Okay? Now, because of this class, we can talk of another field, subfield, which is predictive analytics, no? Hence, prediction is a major outcome of correlation. So when you talk of correlation, you can talk of prediction. Okay? Especially if your correlation based on big data. Okay, that's what's mentioned, right? Mentioned on the in the other slide. All models are wrong, but some are useful. Meaning, as we mentioned there, it can be close as long as it's close enough. No, it can be close enough if you base it on big data. The prediction can be close enough if you base it on big data. Okay, and has led to the research buzz around the subfield of predictive analytics. No. Interwoven time series such as this may be modeled using vector. Now, there's another technical term here, vector autoregression. Now, usually these topics they talk here about this in this conference, no, this convention, PAO, Predictive Analytics World. No, there are entire conventions devoted to this facet of correlation, such as the widely popular PAO, Predictive Analytics World. Maybe a putative collection of people with non-working crystal balls. As William Gibson said, the future is not Googleable. Pattern recognition is in, past causality is out. So correlation is not causality, but yes, it can be pattern. That's just like what we see, right? We can see pattern here, right? So in correlation, yeah, we can talk of pattern, no? But not causality. It's not a cause and effect. Okay, class? So with the rise of big data, companies have realized the importance of the role of data science, no, in their marketing and sales strategy, and the need to ensure data engineer training. No? The explosion of data scattered over multiple online media has enabled data science to develop and create a new professions, among them the data scientist, the data engineer, the data miners, data analyst, data architects. No, training in this sector is increasing, favoring the arrival on the job market of people who are experts and trained in the latest technological developments. No, so they will play a big role, no, in the technological development, big roles. No, but we'll just talk about in the following slides. We'll just talk about data scientists. No, okay, data scientists. But if you're a data scientist, now there's skills of data engineer, data miners, data analysts, data architects that you possess as data scientists. Okay, in the following slides, we'll talk about data scientists. Who is data scientist? Okay, so let's talk more about it. Data scientists. So this is the last part, class. Okay, now we'll talk about real people now. No? Real people. Not just real people, but not ordinary people. There are like popular people, no? In their fields, probably not to you, in their fields. Okay, so let's dive in. Who's data scientist? Data scientist is someone who has unique, interesting questions of data based on formal or informal theory to generate rigorous and useful things. So it's all start from a question, right? From questions. Okay, just like what you experience in high school, right? But of course, in high school, we can say not real question, unproblematic question, because just for you to experience, as I've been repeating, those steps in scientific method. But it's a good, it's a good activity also, But better activity if you're part of a science fair project. So there somehow you experience how to create a real question, relevant question, Yeah, as mentioned here, relevant, So anyway, yeah. Real question, and not unproblematic. Because in a classroom, usually I'm problematic. When I say I'm problematic, not really a problem, In fact, it's already established. The answer is already established. That's why the hypothesis there is 100% already. But in reality, when you say hypothesis, it's an educated guess. So there's a possibility it's not 100% correct. But in classroom purpose, usually it's 100% because you already base it on your readings. No? And the theory, the general, is not anymore unique, not anymore like original. No? Again, the purpose there is only to experience those steps in scientific method. You will experience the real experience in the science fair project, when you create real question, no? And also in college, no, when you do your thesis or dissertation. Okay, class. Okay, it's likely to be an individual with yeah. So data scientist is someone who asks unique, interesting questions of data based on formal and informal theory to generate rigorous and useful insights. No, so that's the purpose. No, rigorous and useful insights. No, can be in business context for profit. No, to lessen the cost and for human care. Okay, so for business context. Now it's likely to be an individual with multidisciplinary training. No. By this time you should know that already, no? Multidisciplinary training in computer science, business, economics, statistics, and armed with the necessary quantity of domain knowledge relevant to the question at hand. Okay, so in the narrower domain of business life, the role of data scientist is to generate applicable business intelligence. Now, again, this is another, remember the text mining? This is another class, data analysis methods that we talk about, right? Business intelligence. Okay, so and in the big data applications, we really see the use, no, in business, no. But of course, not only in business, right? Okay. Now, in a recent talk at the H2O World Conference in the Bay Area on 11th November 2015, well-regarded data scientist Hilary Mason emphasized that the creation of data products, no, requires three components, no. This one class, creation of data products. But again, I'd like to emphasize that it's not only about creation, right? It's also this, not to generate rigorous and useful insights. Okay. Requires three components: data, of course, and plus technical expertise, the machine learning, plus people and process. No? These three. Google Maps is a great example of a data product that epitomizes all these three qualities. She mentioned three skills that good data scientists need to cultivate in math and statistics. In fact, we will tackle this now. But you all know already, no, it's not about statistics only, right? Not only about statistics. And then coding, and then communication. So I'd like to emphasize this point, no, communication, because you might think that if you're a data scientist, you focus more on the books, no? No, you also do this, no? The communication aspect. Because you have to communicate your results well to the stakeholders, no? Those people who will be affected, no, by the results or your findings that you arrive at, no. So this one is important. Coding is to organize your data. Organize your data. This one for the models, no, for the models. But again, it's not only in math or statistics, no. Okay. Anyway, that's according to her only, no. So preceding all this is the ability to ask relevant questions, as I mentioned in the previous slide, no, about the relevant questions, the answers to which unlock value for companies, no, consumers and society, no, because that's why there's a need for this one class, no, because you have to know your context, no. For example, if it's in a company, no, so if you are skillful at this, no, in communication or in dealing with people, not only with books, no, somehow you can arrive at relevant question, no? Relevant questions. Okay, that has value to your company, consumers, and as a whole, the society. No, not only in your industry. Okay, everything in data analytics begins with a clear problem statement. So again, the problem statement, the question, not only relevant but also clear, and needs to be judged with clear matrix, because it all starts there, right? Because your gathering of data, analyzing of data will all be based from the problem statement, from the question, right? That's why they have to be relevant and clear, right? That's very important. Okay. Okay, that's the reason you collect you gather or collect those data, those big data, and then you apply data analytics, na, because of those. You want to answer those relevant questions, or those clear problem statements. Okay, and there should be metrics, no. How can you tell that those questions are relevant or those problem statements are clear? You must have matrix, no. Okay, like way to check whether they're really clear or relevant. Okay, like criteria. Okay, rubrics, like rubrics. Okay, so anyway, to proceed. So being a data scientist is inherently interdisciplinary, no? So not only multidisciplinary, no? Not only knowing all these fields, but also able to interact. That's why interdisciplinary with those people, experts on those fields, no? That's why important that skill, I'm sorry, that skill on communication, no? Because how if you don't talk, if you're just quiet there, how can you interact with them, right? Okay, so you have to deal with real people. So because you deal with real problem, no, not unproblematic, just like what you did in high school. No, it's not in a classroom. No, that's not only for an experience or for training, no. But it's the actual training really is in the work field, no. Or if you do your partially when you do your thesis, no, something like that. But really, after you graduate, now when you work, when you become a professional, no, that's the real real application. But there's a need for training, no. That's why you're here, no. You're in college. Okay. So good questions, no. Good, relevant questions, clear problem statement, no, come from many disciplines. And the best answers are likely to come from people who are interested in multiple fields, or at least from teams that commingle varied skill sets. That's why there's a need for another class, right? Convention, conference. Remember, we talked about that here. The conference, Hillary Mason, no, part of that conference, and then talk about this, no. Talk about these skills, no. So there, no, there's a need, no, for those trainings, no. Even if you're already a professional, you still need to participate in those conferences, symposiums, talks, and so on and so forth. And that's the meaning of being interdisciplinary, no. Not only multidisciplinary, not only about books, dealing with books, but dealing with people as well. Okay, to come up with that real problem, because it all starts from there, no. It all starts from there. Real question, real problem, relevant, no, clear problem statement. It all starts from there. Okay. Okay, class. So and to reach that aspect, you must be multidisciplinary and interdisciplinary. Okay, class. So Josh Wills of Cloudera stated it well. A data scientist is a person who's better at statistics than any software engineer, and better at software engineering than any statistician. So meaning, you're both knowledgeable about this too. That's why you can communicate with those statisticians and even software engineers, no? You can communicate with them very well because you have knowledge about this too. These two fields, no? So that's why multidisciplinary and interdisciplinary. In contrast, complementing data scientists are business analytics people, no, who are more familiar with business models and paradigms, no. Usually when we talk of data science, we associate it with business, business. Okay, class? But again, when you talk about business, not only profit, not only cost, but also human care. Okay, so a good data scientist will be adept at managing volume, not just technically in a database sense, but by building algorithms. We talk about algorithm analysis, right? So very important. This is like a form of model also, no? To make intelligent use of the size of the data as efficient as possible. Usually, class, the algorithm in your course, right? Computer science major, no? Computer science related course. But the model that we will talk about is not actually algorithm, more of not a program, no? In the following weeks, no, statistics, no, in the form of equations, no. Okay, and we all know that if you're a data scientist, you're not only skillful at that, you should also be skillful in algorithms. That's why it's necessary that you have a computer science related course. not only statistics, because you're not only dealing with models, no, as well as algorithms. That's why last lesson we talked about algorithm analysis, no, and it's kind of what advanced, right? What we talked about last time, some abstract concepts, no, mathematical concepts. So anyway, that's why this time we're talking of later. Yeah, we're talking of real people now, no. So to emphasize the point also that it's not when you're a data scientist, it's not all about those mathematical concepts, no, or those algorithms, no. No, you deal with people, no. Okay, so let's talk first about the what's this? Anatomy of a data scientist, no? Before we talk about real people. Okay, anatomy of a data scientist. In terms of salary, average salary of data scientists is $120,000 per year. So if you compute that in pesos, say $1 is 50, but we know it's higher than 50, right? So just say for computational purpose. So 120 times 50 is like 6,000, right? So this is like 6 million per year. But 1 million a month, 6 million, but there are 12 months. So 500,000 in a way, no? 500,000 pesos per month. Among the three class, data scientist, data analyst, data engineer, the highest, no? Data scientist. Next is data analyst, and then data engineer. Okay, when it comes to the anatomy, okay, or the salary particularly. Now, education. 88% of all data scientists have at least master's degree. Okay, 46% of data scientists have a PhD. Okay, then benefits. Harvard Business Review called data science the sexiest job of the 21st century. Na? One of the fastest growing careers in the United States. 94% of the data science graduates have found jobs since 2011. So they're in demand. No? Skills, yeah, we mentioned this, right? The programming languages, then statistics. That's our focus in the following weeks. Okay. Then multivariable calculus and linear algebra. That's why you have a background in calculus, right? And then linear algebra. Linear algebra is the vector algebra that we talk about in the, I think, third lesson, no? The mathematical preliminaries. When we talk about matrix, no? But of course, those are only basic, no? Basic. There's a course, linear algebra. Okay, so machine learning. Okay, software engineering, wrangle, visualize, and communicate data to management. Okay, the word communicate, now communication. Okay, responsibilities, conduct research, extract, clean, and analyze data from varied sources. No, clean, I think we talk about that, the cleaning of data, no? In the first two lessons. Solve problems, build automation tools, the AI, no? Communicate findings to management. So again, the communication skill. Career possibilities. The majority of data scientists work in the technology industry, no? But of course, not only there. Other options include marketing, consulting, healthcare, and pharmaceuticals, finance, government, gaming, and many more. So they're really in demand. No? Okay, now let's talk of real people. As I mentioned at the beginning, no? First, let's talk about DJ Patil. Excuse me, Danner J. Patil. Born August 3, 1974. Is American mathematician and computer scientist, no? Who served as the chief data scientist of the United States Office of Science and Technology Policy from 2015 to 2017. He's the head of technology for Devoted Health. He previously served as the vice president of product at Relate IQ, no, which was acquired by Salesforce.com, as chief product officer of Color Labs, and as head of data products and chief scientist of LinkedIn. I think you know LinkedIn, right? Okay, his father, Suhas Patil, is a venture capitalist and the founder of Cirrus Logic. Now, this word data scientist, coined by DJ Patil and the other data scientists, now we'll talk more about this too later. The title data scientist, they coined it only 6 years ago. This time, I think this time, where I got this information, I think this was 2014. So 6 years ago, 2008. So they coined the term data scientist last 2008. No? And this this title has grown to prominence in recent times. No? Indeed, data scientists are some of the most sought after people on the planet. Companies like Google, Facebook, LinkedIn, and Netflix have relied heavily on their expertise of data scientists to help navigate and better understand the vast amount of data being produced, or the big data. No? The role, however, is not exclusively statistical. As I mentioned, no? Though we will focus in the following week statistics, but again, it's not all about statistics only. No? It also requires a visionary, insightful, and imaginative individual that has the ability to see solutions within the data and find the most pressing problems that business face. Okay, now let's talk more of the other 7. Actually, it's also mentioned this too, no? Mentioned also in the following slides. So let's who's the top? Because they're the second, no? When it comes to the ranking, they're the second top data scientist. Who's the first one? Okay, here's a brief summary. So in an article on Forbes, November 10, 2011, Team O'Reilly highlighted 7 of the most exciting and powerful data scientists today. Here's a brief summary of the chosen 7. This 7 class can be paired, no? Like this, pair, so it's counted as 1. Okay? The others also pair, but the others individuals, no? Just like the first one, who is Larry Page. So you notice popular, probably the technology. No? I don't know if you know him, Larry Page, but in his field, he's very known, especially he's the CEO. Chief Executive Officer of the Google. And Google is very popular, right, to us because we use that. And a while ago, we just talked about Google flu trends. No? Also ranked as the 13th most powerful person by Forbes last 2013. Page built Google with Sergey Brin while studying for a master's in computer engineering. No? So this is the master's. No? He took a master's course in computer engineering at Stanford University. He's the inventor of PageRank, an algorithm used by Google that ranks the popularity of web pages in their search engine results, and is a pioneer of data analytics. No? So he's a pioneer of data analytics, no, that we talked about a while ago. With an estimated 184 petabytes. No, we're hearing another word, no? Petabytes. Before we talk about exabytes, terabytes, now petabytes, no? Petabytes of data produced each month. To be honest with you, it's my first time to hear these words, no? Because I'm more familiar with the megabytes, no, with the gigabytes, but not the other, the other, what do you call this? Prefix, no, peta and so on. Okay, 184 petabytes of data produced each month. Now, Larry's vision in 1998 has placed him at the head of the largest database on the planet. Okay, class, the following pages, I'll just read them because we're running out of time. Anyway, self-explanatory, so I'll just read them, no, not discussed anymore. Okay, so next is the second. Yeah, as I mentioned, they're the second. Jeff Hammerbacher, Chief Scientist at Cloudera. DJ Patel, Entrepreneur in Residence, Greylock Ventures. Hammerbacher and Patel coined the term data scientist, as mentioned. Now it's Silicon Valley's hottest job title. These two built the first formal data science teams at Facebook and LinkedIn, respectively. Now at Cloudera, Hammerbacher has been key to driving the success of Hadoop as a standard tool for processing large unstructured data sets, now with a network of commodity computers now. Now, Patel, as a data scientist in residence at Greylock, is seeking out the next generation of hot data-driven startups. Who's the third? Now, again, pair, no? There are what? Professors, no? At Stanford University, but online, if I'm not mistaken. No? Sebastian Thrun and then Peter Norvig. No? When Thrun and Norvig decided to teach their Stanford course, Introduction to Artificial Intelligence, over the internet, they managed to sign up over 140,000 students and prove that AI is no longer just an academic subject. Norvig is Google's chief scientist. No? Thrun is leading Google's efforts to build a self-driving car that relies on AI algorithms and the memory of hundreds of thousands of miles driven by Google Street View vehicles, recording and measuring everything they saw. So who's the fourth? Now, she's the only, among the 7, she's the only female, no? She's the only female. But it doesn't mean that there are no other data scientists who are females, class. No, in fact, there's Hillary Mason, right? The one we talk about. And there are a lot. It's just that there are more men than women. Okay, so Elizabeth Warren, at this time class, candidate, but I don't know now. Anyway, the banking system excesses that led to the economic crash of 2008 are an example of big data gone wrong. As the provisional head of the Consumer Finance Protection Bureau, Elizabeth Warren began the job of building the algorithmic checks and balances needed to counter the sorcerer's apprentices of Wall Street. Okay, in her campaign for the U.S. Senate, she promises to continue the fight. So maybe you can search about this. Is she now a senator? Because at this time, class, still a candidate, no? So anyway, but still, I believe she's still a data scientist now. Okay, next. Now, this one doesn't look like American to me. probably naturalized American. He's more like an Asian, right? Todd Park, and also the name. CTO. CTO, if there's CEO, Chief Executive Officer, is the Chief Technology Officer, CTO. At Department of Health and Human Services, Park is leading the charge to transform American healthcare into a data-driven business. No? From medical diagnostics to insurance investment to community health statistics, he's finding ways to use data to make healthcare more effective and affordable. We talked about healthcare a while ago, right? The healthcare industry, when we talk about those three elements of the data analytics. No? Okay, so next is Alex Sandy Pentland, a professor at MIT. No? Among one of the most cited computational scientists in the world. Okay, so Sands is a professor at MIT. He colleagues the big data and personal data initiatives at World Economic Forum and is a founding member of the advisory boards for Nissan, Telefonica, and Motorola Mobility. He's considered to be one of the biggest pioneers, no, of big data. Pioneers of big data. Okay, a while ago, we talked about pioneer of the data analytics, Larry Page. No? This one, pioneer of big data that we talk about also, right? In this lesson. Okay, mobile information systems, computational, social science, and technology for developing countries. Okay, next is the last one. They're the last pair. Okay, Hod Lipson and Michael Smith, computer scientists, now Cornell University. In 2009, both Lipson and Smith were responsible for the groundbreaking software called Eureka. It's an AI for program class, no? Software program. You can see the pendulum here in the picture. Their contributions and development of the software are considered to be the first theories of robotic thinking. By monitoring the data produced by physical systems over the course of a few days, Eureka can describe the natural laws that govern such systems. Now, their work has received global media attention, has been covered by the New York Times, Slate Magazine, the Wall Street Journal, CNN, among others. These are just the top, but of course there are other data scientists who are, I think, successful also, no, in this field. No, not only this seven. No? Okay, class. These are the website references. So you want to explore more about this, you can screenshot and then also this. Okay. Okay, so that ends the lesson for this week. Thank you very much for attending.